Hello everyone, and today we are moving beyond conventional academic cases to explore the strategic complexities of a facility optimization. In the field of industrial engineering, facility planning is far more than a spatial arrangement. It represents a critical investment decision where tangible fixed assets must align with long-term organization goals. As we know, facility location decisions are infrequent, involve high non-recoverable costs, and ultimately dictate a firm's competitive capacity. The case I am presenting today focuses on a modern e-commerce distribution network. This is a classic discrete space location problem, where we evaluate a finite set of feasible candidates to establish a strategic node in a supply chain. Let us define specific problem anatomy. We are tasked with evaluating three candidate cities: Eskişehir, Afyon, and Konya. These cities were chosen not by chance, but because they represent the primary logistic corridor connecting our four major demand centers: Istanbul, Ankara, Izmir, and Antalya. It is important to distinguish this from a standard transportation model. We are solving location allocation problems. This is a dual-layered decision process. In location phase, we can ask which specific node should be activated. And in allocation phase, we can ask how should the material flow be distributed to satisfy market demands at the minimum cost. By utilizing a single facility policy, we are searching for the absolute global optimum within a feasible region. You can see our GAMS model. So we can deep dive into the engineering logic of my GAMS implementation to achieve high fidelity decision making. I utilized mixed integer programming, and I defined indices I for candidates and J for markets. This ensures the model is scalable. We could add 100 cities without altering the mathematical structure. Our binary decision variable yi is the heart of our model, and I introduced a binary variable that acts as a logical gate. If yi is equal to 1, then facility is active. If yi is equal to 0, it is inactive. This allows the solver to handle discrete choices. And you can see our constraint M, big M linking constraint. This is a sophisticated modeling technique. By using a capacity upper bound or big M, we enforce a logical dependency. It ensures that no material flow X can originate from a site unless that has been activated by our binary switch Y. In this case, M is set to 2000, acting as safe upper bounds. And for our objective function is our goal to minimize it, which is the total weighted distribution cost. So as we solve our GAMS model, we can see normal computation to prevent global optimum of 18,700, and solver established that Eskişehir is 1000. This is the result of rigorous mathematical trade-off. And mathematically, Eskişehir acts as the center of gravity for our specific demand distribution. The logic of efficiency minimizes the weighted distance to our high-volume markets, specifically Istanbul and Ankara, where 65% of our total demand is concentrated. By selecting Eskişehir, the model mathematically bypassed Afyon and Konya because they couldn't provide the same logistics synergy for the specific cost-demand configuration. And the mixed integer programming set use confirmed that no cheaper solution exists for this network. As conclusion, we can say this project bridges gap between raw data and strategic facility planning. As we have observed throughout our current academic framework, facility planning remains the most significant opportunity for cost reduction and productivity improvements. By mixed integer programming, we have moved beyond the subjectivity of traditional factor weighting methods. We are providing mathematical certainty for investment that represents measured tangible fixed assets. However, as engineers, we must remember that the facility is a dynamic entity, while 18,700 is our optimum today. Our model shows a decision support system that can be run as fuel costs fluctuates our dimensions. And so, thank you for your attention. I'm now open to technical questions regarding the model's logic or results. See you next lesson.